Hey, greetings and welcome, friends. Me and really, you can't disprove that these are my best friends that I'm with right now making this video for you. But we're going to do some proofs for you today. And today we're going to be proving triangles congruent, specifically. We've been able to prove figures congruent by saying if I could show that every pair of corresponding sides and angles were congruent, then the figure was congruent. But that's a lot of work. And mathematicians, as efficiently lazy people, want to find shortcuts. And that's one of the things we'll do today. So we're going to look at the side-angle-side congruence theorem. It says the following. If two sides and the included angle, this is muy importante, all right, muy importante, mis amigos. The included angle of one triangle, bless you, are congruent to two sides and the included angle of the second triangle, then the two triangles are congruent. So notice for triangle ABC, AB is congruent to DE, AC is congruent to DF, and the included angle, Ryan, if you notice, is the angle in between those two sides. All right, so this angle, for instance, would have been a non-included angle between those two sides. So that's what they're referring to, included. All right, so yeah, so I was just asked the question, what if this was the arrangement I had? And instead of side angle side, we would have had angle side side, and that there's no ASS congruence theorem in math, guys. That's inappropriate. It's inappropriate and false, conveniently. Yes, so that won't work, but we will, throughout this chapter, discover some additional congruence theorems that we can apply to triangles. All right, so big idea here is it's got to be the included angle. All right, is the big idea. So, so the proof of this, I'm actually back in the day. I'm used to having started with a different theorem and then proving this differently. But we're actually going to prove this for you using transformations. Yes, it's going to be great. So step one, let's translate. All right, translate. Right, because I can show that two objects or two figures are congruent if there's a congruence transformation between the two, right, that map them onto each other. So if I translate triangle ABC to, or let's say by, maybe it would be better, vector AD, right? So if I map this by vector AD, I can now map them onto each other, like so. Yeah, I can map it any way I want. All right. So then it would look something like this. I think you guys agree, right? Something like this. All right. Step two. Numero dos, even. Excellent. Rotate, I guess we could call it triangle A prime, B prime, C prime now. About point D, so about this point. By, let's see, what, actually I'm going to write it down here because I'm running out of space. By angle, let's see, so I guess, yeah, I'm doing counterclockwise by the angle, this angle here. All right. I guess I could call that, they call it C prime DF. The prime letters are going to be the blue triangles letters that I don't have labeled here. So this would have been B prime. Yeah. All right, don't worry, it'll be okay. So if I rotate that, now I'd be left with a purple image like this. All right, so I managed to have it line up exactly on this line, and now this would be a double prime. B prime is now all the way over here at B double prime, And this point would be, it was C prime, so now it's C double prime as well. Okay? I guess I could also specify it was counterclockwise. And let's see, lastly, what do you guys think I could do to get this purple shape to match up to that white shape? Yeah, let's reflect. Right now that's triangle A double prime, B double prime, C double prime, over what line segment or line? Yeah, over DF, or over A double prime, C double prime, right? But I'll just call it DF. And that's going to map it onto itself, right? Or it's going to map it onto that. This angle will match up to that angle. This side is congruent to itself. This side we already knew was congruent there. And then it turns out that EF and B prime C, or B double prime C double prime will match up. So then I could conclude that because there is a similarity transformation, right, or since there is a similarity transformation that maps blah, blah, blah. Let's see, is a similarity transformation. That maps one to the other. Or, oh, error! Guys, you should have saved me. This is congruence. Yeah, I just stole that point back from Liam Math. He was eating bugles. Alright, that maps one to the other. Then triangle ABC is congruent to triangle DEF. And the reason that's true is by definition of congruent figures, so that we had a biconditional statement there the other day. So I'm not ever going to ask you to like recreate this proof. I'm just showing this to you so that you've got a sense of believability in the side angle side congruence theorem, which also we will abbreviate SAS. There is not a Geometry 2 course that I've heard of, but you can take like geometry in college. True. Right. There are lots of other geometric concepts that are not seen in a regular high school geometry course. All right. So, Holden, we're going to do this example here. We're going to use side angle side and write a new proof. And this is now, we are in the forest of proofs. We have entered into the wonderful, fruitful wilderness. And we're going to do more than survive. We will thrive out here in the land of proofs. This is going to be amazing. I love it. Are you guys ready for this? I love it. Let's do some statements and reasons. Two-column proof, my favorite. All right, so I've got this little figure here. I might say it looks like a parallelogram. It looks like a parallelogram. We can't prove that yet. Well, I could prove it, but seriously. But anyways, let's see. So let's start with our gimme information. So given information. And guys, this is super cheap, but look at what I let you do. I just say ditto, right? Just copy. Yeah, you know what I'm saying. You know what I'm saying. And when you label information as a statement, it's not a bad idea to label it as well on your in the figure, in the diagram. And sometimes be aware that there might be labeled information in a diagram that maybe wasn't listed, and you could still call that given. So I've got this quadrilateral and a diagonal, and I've been told that I've got a pair of parallel and congruent sides. And so if I'm going to use side angle side, right now it looks like I've got one of those. I've got the S done. right? I've got a pair of sides that are congruent. What's something else I could say? I'm gonna need an angle and another side. Yeah, AC is congruent to itself. I actually like that you said AC is congruent to CA, kind of anticipating how these will line up to each other. But if someone just said AC congruent to AC, I'm fine with that as well. And the reason that's true is the reflexive property. Yeah, technically of congruence. I'm fine if you just write reflexive. And so we could label that congruent to itself. So now I've got two sides congruent to two sides. And there is one angle that will suffice. So I don't want this angle. I don't want that angle. I'm going to need to show this angle is congruent to this one. Is there a way I can do that? Aight. Wow. With the swiftness. Aight. Alternate interior angles theorem. Let's see if we can name those angles. So that is angle ACB, or BCA. I'll call it BCA. Is going to be congruent to angle DAC. Oh, there you go. Breast cancer awareness. Here we go. Do I have enough information to prove these triangles? I think I do. I think I can say that triangle ABC is congruent to triangle. And now, when I name the triangle, there's like 6 ways I believe I could have named this triangle. But once I name one, I need to make sure that this name corresponds, that all the corresponding letters match up. So angle A in the triangle ABC matches up to angle C here, and then I've got to go to the away point, yeah, CDA. And they did give it to me here, but I just want to point out that it matches up. And the reason this is true is side angle side congruence theorem. All right, but I'm fine with you just saying the side angle side. All right, let's jump to another one. Good old proofs today, friends. This is great stuff. I believe it because it's true. All right, so here we are. Statements and liaisons. I'll start with something like that. All right, so it says in the diagram, QS and RP pass through the center M of the circle. What can you conclude about triangle MRS and triangle MPQ? Okay. So let's see. So the only thing I know is that there's a center. I'm just going to say given. Right, they pass through the center. There's a circle. Yeah, we're good. We're good. What is a statement that I can make? SM is congruent to MQ. Well, they didn't actually say it was a midpoint. It's the center of a circle. This is the diameter of a circle. I might actually just kind of call that definition of circle. All right, or you could even call it a definition of a radius. A radius is any segment that goes from the circle to the center, right? That would be fine. So I could actually say those are congruent. And actually, I could even say this. Or you could have written this on a different line. I actually know not just that these are congruent in pairs, but that all 4 are congruent to each other by definition of circle, right, or radius, right? Right, that all points on a circle are the same distance from the center, so they are all congruent to one another. I don't have enough information to show these triangles are congruent yet. What else do I need? PMQ, yep. Yeah, you could have said QMP or PMQ. It doesn't matter in this case. Actually, these triangles kind of will have a symmetry to one another, not just a congruence. So there's multiple ways I could name these. PMQ. And the reason that's true... Vertical angles theorem. Those angles be the verticalist of angles. Yes. So yeah, and then I think I have enough information that I could say triangle MRS, Mrs. Triangle, is congruent to triangle, let's see, MRS. So I've got to start at M here, and I could say MQP or MPQ in this case. Either way. And the reason that's true is side angle side. Side angle side. Man, good stuff. Ooh, here's a Vermonty looking problem. Example 3. I'm gonna skip some around some. Let's get us to some class question today. Absolutely worth it. Yeah, your picture in black and white might not show up as well. But it says, you are making a canvas sign to hang on the triangular portion of the barn wall shown in the picture. All right, so you're gonna like literally make, okay, all right, good for you. You think you can use 2 identical triangular sheets of canvas. You know that RP is perpendicular to QS. All right, so perpendicular there, okay. And that PQ is congruent to PS. All right, so those are probably 2 assumptions that you couldn't make about most barns in Vermont anymore. Right? But some might say that the beauty of those barns is the fact that they are a little bit dilapidated. So, all right, here we go. Let's start with these. So RP is congruent, is given, and RP is perpendicular to QS, and PQ is congruent to PS are the givens. I don't make you rewrite those. So I've got this and this. I've got this. All right. What's something I can do? Now my goal is I'm trying to prove these 2 triangles are congruent. There's actually multiple reasons that go into it. I'll alley-oop it if you want. Straight angles theorem. The one that, yeah, the made-up one. Okay. All right. The reasons that these are true, this is true, is because of def of perpendicular lines. All right. As well as that they are right angles by definition of right angles. Angles. And, yeah. And those are, yeah, all right angles are congruent. All right. So there you go. All right. Now what could I say? Oh, classic. RP is congruent to itself. I think Jordan agrees. Let's see. And that is true by the reflexive property. And yeah, I think we've got enough. We've got our side angle side. So this is way better than having to have proven all 6 pieces of information, the 3 corresponding sides and the 3 corresponding angles. I can now do it with just 3 of those things. So yeah, so triangle PQR is going to be congruent. So yeah, PQR to PSR. Yep. And today's only reason is side angle side. And we did in fact have the included angle, right? This angle was in fact between the sides that I was talking about, yes. And so the convenient thing about these names of these theorems is that, notice the angle is in between the S's, and that is in fact where it's found in the diagram as well. All right, do I have one more good one for us? Ooh, a construction? Let's do it. Let's do a construction. I think you guys have this one as well. I haven't been doing my constructions in the videos lately, but I think I will. Okay. Ah. All right. Let me warm up the old elliptical tool here. Bleep. It's always wrong when I start it. I wish I could like default it. Wait, did that just like warp? Oh. Wait a minute. If I double tap that, it warps it to a circle, guys. I just learned something new. How sweet is that? I'm really excited about this. I'm glad that all of my friends in real life are here with me to celebrate. Wow. Wow, that was amazing. I'm excited. Let's see if we can do this. So it says start out with drawing. I'm gonna just draw mine right over their answers here. All right, let's draw some line or something. I'm even gonna draw mine at an awkward angle here. So here's some line, like so, and they need me to match that to a length. All right, so I'm gonna pick a point on that line. We'll call this D. And now I need to find a point E units away, and I'm gonna make DE, congruent to AB. So I could do that by using my compass tool, line it up at A, expand it, and match my radius to being the length AB. Something like. And now if I drag this over here and swipe, there's going to be a point E. Lovely. Okay. And now they ask us to construct an angle. Okay. Construct an angle. Right, that is going to be congruent to this one. That's what I'm aiming for. So if I want to construct this angle, I could actually, well, I'll do a different arbitrary measure. So let's see, let's go over here. Like so. I'll pick a different measurement. I'll do these in a different color. Theoretically, you could have done the same. You could have just mapped the arc that I just did for E over. And so I do that, and then I line this up with the intersection of my arc. Right, this is one that I always have to remind myself of as well. Just like, all right, how's this working? Yeah, this makes sense. And I line it up there, make that swipe. Right, so I changed the radius like so. And then if I do this over here and swipe, that intersection is now something that I could pass it through to get a congruent angle. Something like so. All right. So now that means that I have two angles that are congruent. This guy's congruent to that guy. But I need to know how far out on this ray I should go. And so we're going to construct a side. And we'll use our compass tool again. Good old times. And so I match up my center at A. I change the radius to be equal to C. Notice this is a scalene triangle. Otherwise, C and B would both be on the triangle. So I'm going to match this radius with this over here, like so. And so here's a new point that I could call F, and it is DF is going to be congruent to AC. And now I think I can just finish drawing my triangle. All right, so let's, I'll make my triangle yellow. There we go. Like so, and like so. So notice the pieces of information I used to create this congruent triangle were simply two sides and their included angle. And if you then go back and measure the sides of your triangles, you'd find that they're all corresponding and congruent, as well as the angles. All right, thanks for watching, Internet friends. Adios.